Have you ever seen animations like this? YouTube is filled with these animations with thumbnails like the visualization of the irrationality of pi. If you're like how I was, you know what that sentence means, but you don't quite understand the point. I'm Cypher, and today I want to show you a simpler version of this animation as well as explain what it means to visualize the irrational nature of pi. Now imagine a circle. Pick a point at angle 0 and put a dot there. Rotate ahead by a certain angle increment and draw a line by moving the dot ahead. We want to see how long it takes for this small dot to return to its starting point. We can mathematically explain this by saying we have a series A and the 0th element of that series is 0. Of course it can be anything, but we just happen to choose 0. Now we increment it by a chosen amount every time, meaning when we want the third element of the series, we add our increment 3 times. So the equation is a of I equals a of 0 plus our increment times I. A circle has 360 degrees or 2 pi radians, so everything after that just repeats. So to keep things clear, I'm going to add a little percent symbol to our equation along with 2 pi. Those of you who are programmers recognize this as the modulus operator. It means we divide everything by 2 pi and we only count what's left over. So 5 modulus 2 would be 1. This way we can see the exact angle position of the point within a 0 to 2 pi range. And we have our equation. Are you starting to see the problem? If you're not, then let me explain. As you know, irrational numbers are numbers that go on forever after the decimal point, like pi. Two important rules about these irrational numbers is that addition, subtraction, multiplication, or division between two rational numbers always creates a rational number. But between an irrational number and a rational number, the outcome is always irrational. Since I is a rational number and pi is irrational along with all its multiples, as long as our increment is rational, we can't ever land on pi using our equation. And of course the same is true of 2 pi, which means the dot might move infinitely close to 2 pi, but it will never land on it. It will never return to its starting point. In order for us to return to any element in this series, not just the starting one, we would have to add or remove 2 pi from that element using our increment. And since we've already shown that's impossible because our increment is rational, not only will the dot never return to its starting point, it will never return to any of the points it's ever been on before. The dot never passes the same point twice. It will get infinitely close to some of the last points. So close, in fact, that the pixel detail limitations of the screen might make you think that it's done it, but seeing as we proved it can't ever do a 2 pi rotation from any starting point, it will never land on a point it's landed on before, and it will never create 2 parallel lines. This function creates an infinite series of unique numbers between 0 and 2 pi. And especially if you pick an increment that's really close to, say, pi over 2, the point will just barely miss the beginning as it does a full rotation. These videos are also showing this specific property of the number pi, just differently and using complex numbers. Subscribe if you like creative coding or math.